We are live now.
Hello everyone. Welcome to the fifth and final session of webinar series conducted by Team PROTOLITH 20, constituting the student body of Department of Earth Sciences, IIT Bombay. We have a very special person among us today to share a few droplets from the ocean of his vast experiences about his phenomenal and accomplished research career. As Hungarian biochemist Dr. Albert quoted, research is to see what everybody else has seen, then think what nobody else has thought. This quote in itself suffices to highlight the significance of the work done by academicians like Dr. Shankar himself. I would now request Professor M. Radhakrishna to introduce our keynote speaker to the audience.
Good evening, all students. I welcome Professor R. Shankar for this very interesting and very enlightening lecture on how research should be done to educate all young minds, inspiring minds towards very quality research, how to think and apply and carry on high quality research. Here, Professor R. Shankar is formerly professor at Mangalore University. He's a professor of marine geology, retired from active service in 2017. He had a distinguished academic career, and I'm happy to inform that he is one of our alumni 1977 MSc Applied Geology passed out, and then he is also one of the Institute medal winner as a first rank holder of his batch. And Professor Shankar has been as a Commonwealth Academic Staff Fellow in 1991. He won several awards. To name a few, he has been National Mineral Award in 1994 and C.V. Raman Award in 1998, Young Scientist Award of Karnataka Association in 1995. He has been, as an eminent academician, he served his outreach and educational activities are very excellent. He has been member of organizing committee and chaired the Geo-Host Committee of our 36th International Geological Congress 2020, which is supposed to be held in Delhi. And he has been chair of an International Geoscience Education Organization during 2014 and 18, and he has been member of IUGS Commission on Education, Outreach and Technology Transfer, and a national coordinator for Excellence Olympiad up to 2013, and he has been foreign secretary of Geological Society of India during 2004 to 16, as well as has been serving as a council member during 2001 to 2004 in the Geological Society of India. And then several international bodies an important assignment he has been holding. And he was the founder research coordinator of Ocean Technology Cell at Mangalore University. So I do not want to take more time. The list is endless. But we have here one of the distinguished academician to share his valuable experiences and insights and to encourage the young minds. Thank you, Professor Shankar.
Many thanks, Dr. Radhakrishna, for your kind words of introduction. Good evening, friends, ladies and gentlemen. First of all, I would like to compliment the organizers of PROTOLITH for putting up a useful and enjoyable event for our students across India. And in particular, I would like to thank Dr. Radhakrishna for the gracious invitation to deliver today's talk. It's always a great pleasure and excitement for me to come back to my alma mater. But this time it is online for obvious reasons. And I'm also happy because this program brings me in contact with students, and students are dear to my heart. So my presentation will be a 3-in-1 shot. First is, I'll share the results of our research, which is a new type of investigation. And second and third, I will let you know at the end of the talk. Let me give a broad outline of my talk today. First, we will see the Indian monsoon and its importance, and how rainfall estimates are obtained, and our attempt at Mangalore University to do the same using magnetic susceptibility. We obtained data from 2 southern Indian lake sediments. We'll look at rainfall susceptibility correlation and see support from historical records and other proxy data from other parts of India. There's also some geochemical data in this regard, and we'll reconstruct paleomonsoonal variations in the lake region. We'll see if the sun has an influence on monsoonal rainfall, and finally some concluding remarks. Well, we all know why monsoon is important. Our economy, our agriculture are principally dependent on monsoon. Good monsoon means, you have good crops and people are happy, the economy is on the upswing, upbeat. Lack of proper rainfall, there will be drought and suffering for people. And if too much rain is there again, there will be flooding, loss of life, etc., etc. Therefore, it's very important to forecast the monsoon. And if you want to forecast the monsoon, what we need is paleo-monsoon data. We look at that. And then several proxies have been used for predicting the monsoon of the past times. Some scientists looked at the winds then because it is the southwesterly winds that bring the monsoonal rain. Others looked at primary productivity in the Arabian Sea. Yet others looked at the terragenous input because this is also linked to how much rainfall is there on the Indian landmass. And other people looked at salinity variations because more rainfall means more river runoff and salinity will be reduced. But in all of this, there is a very important lacuna, friends. And what is that? All these proxies are indirect and they are not a measure of rainfall per se. They are all indirect. So we wondered whether there can be any proxy to fill this lacuna. Therefore, we explored magnetic susceptibility. Therefore, we explored magnetic susceptibility as a potential candidate in this regard. There seems to be something happening here. Okay. So,
Fine.
sorry?
Everything is fine. Go ahead, please.
Okay. The hypothesis that we ask ourselves is, can magnetic susceptibility be used as a proxy for rainfall in the tropics? I emphasize tropics because this has been done for temperate regions, but in the tropics, no such attempt has been made. We looked at sediments from 2 lakes, Timannaik and Kere for short, EK in Karnataka, and Pukot Lake in Kerala for short, PK. But we also studied several other lakes, so maybe very briefly I'll mention those points. So these are only 2 in detail now, right? First, Timannaik and Kere, this is near Chitradurga, my hometown, that is Chitradurga city, that's the lake. And this is the fort. During my childhood, I played in that region as a kid, but I never thought that I'll come back here sometime in the future to carry out research. So that's the temperature range, and look at the rainfall, it's meager, it's measly 640 millimeters per year. But most of this is received during the southwest monsoon, that's important for us. That's the Pokot Lake in Kerala. It receives 4,000 millimeters rainfall, again mainly during the southwest monsoon. Then briefly the samples and methodology, we obtained samples from a pit, and all the details are here. I'll not go into the details. I'll pause for you to have a look at those details. Okay. Now let me show is an environmental magnetic approach suitable for this study. Let's look at this aspect. Now, what is the source of sediments and magnetic minerals into our lakes? It is hills to the south of the lake here. Those are the hills. And in the case of Pokot Lake, there are several hills around the lake. So those are the source. But please note that all these things come from nearby regions, not from long distances. If sediments are brought from long distances, you'll have a mixed climatic signal, and you cannot build a proper story of the past climate, right? And in tropical regions, as you know, chemical weathering is dominant over mechanical weathering. Also, there is strong pedogenesis. When we look at pedogenesis, this is principally controlled by climate. And the two climatic parameters that control pedogenesis are rainfall and temperature. Basically, what happens in pedogenesis is iron in the non-magnetic minerals is transformed into pedogenic magnetic minerals like magnetite and megamite. So initially, the iron was non-magnetic, but after pedogenesis, it is strongly magnetic. So you see, this is what happens. Suppose there is high rainfall, this leads to more amount of pedogenic magnetic minerals getting formed, and that will result in high values of magnetic susceptibility and another property called frequency dependent susceptibility. And if the rainfall was low, this will be less, and the values also will be low. So let's look at this pedogenic magnetite. These are fine-grained pedogenic magnetite crystals from a proxy profile. It's a TM photograph, high magnification, that is 50 nanometers on the scale there. Now, in order to prove all this, we have got to rule out certain possibilities, because the magnetic signal in the lake sediments can be for various reasons, not just the heterogeneous sediments brought from the catchment. So what are we going to rule out? The presence of gregite, the presence of bacterial magnetite, the presence of anthropogenic magnetite, and we have to rule out also dissolution of magnetic minerals. Because if magnetic minerals dissolve, then your climatic story will be incomplete. So let's see whether these things are there in our samples. First, is gregite present? There are certain magnetic ratios which will help us find out if it's there. So our data suggests that all these ratios are much less than the threshold values, therefore there is no gregite. Is bacterial magnetite present? Bacterial magnetite looks like these bullet-shaped magnetosomes. And again, there are threshold values. Our values both for TK and PK sediments are much less. Therefore, there is no bacterial magnetite. Then there is also a plot, by which we can find out if bacterial magnetite is indeed there. If it were to be there, it will plot in this region, in this region. So our samples are plotting here and here. All this is for soils and paleosols. and catchment derived materials. And dissolution is also ruled out because all the parameters and values co-vary in both the lake sediment cores. Next, let's see if anthropogenic magnetite is present. And even if it is present, it will be in the MD or multi-domain grain size. There are no industries in the vicinity of the two lakes, and the two lakes are located far away from urban areas and at an elevation. Therefore, based on our data, there is no anthropogenic magnetites. If anthropogenic magnetite were to be there, you'll find this type of spherules, small spheres. This is a sample from a roadside topsoil, so you can see all these spherules from automobile exhaust sitting in the soil. Now let's consider whether magnetic susceptibility can be used as a proxy for paleo-monsoon or past monsoon. So far we have made out a case for susceptibility being principally derived from the catchment, not from those other sources, right? Next, we will examine if susceptibility is related to climate at all. So we look at correlations of susceptibility with instrumental rainfall data. About 200 years ago or 150 years back, several rain gauges were established across the country, and all of these rain gauges have recorded daily rainfall data. So we have all these archived in IMD and other organizations. Then there are historical records with which we will correlate, and also with proxy rainfall data from other parts of India. Okay. So first, let's look at the comparison of susceptibility, red curve here, red curve there, with instrumental rainfall data. See, this is for Chitradurga station rainfall, that is the peninsular India rainfall. Look at the correlations, 0.45 and 0.65. In fact, it is able to record, susceptibility is able to record the regional rainfall pattern. And this is for the other lake, 0.39, 0.44, 0.38. Considering the number of samples, it is still a good, statistically good correlation. Now there are some historical records to support this proposition. What is that? This is the upper part of the susceptibility profile. Ladies and gentlemen, please note this drought period and this high rainfall period. The drought was in 1876-80, the high rainfall was in 1741. There's another one, high rainfall period at AD 1640. Okay? So let's first look at the 1876 drought in Chitradurga. What records do we have? Okay, we looked at the lower susceptibility in the profile. There was a seer or Swamiji called Hebbadu Rudraswamy who set up porridge centers to feed the poor people during this drought. And when the 19-year-old Prince of Mysore, Chamaraj Wadiyar, was coronated, he honored several people in the region, in the kingdom. And one of them was Kashi Annappa Shetty from my town, Chitradurga, for feeding poor people. So there are clear historical records that there was a drought in 1876. Now let's look at the abnormal rainfall periods in Chitradurga. First let's recall that the average annual rainfall is a mere 640 millimeters. But in AD 1741, there were 28 days of incessant rains. It's unbelievable for people of Chitradurga, but it has happened. There is a historical record to say this. So there was so much rain that people called it mad rains. And this high susceptibility value here coincides with one total solar irradiance maximum between the Dalton and Maunder minima in the Little Ice Age. So that supports the data. And secondly, the same 1741 high rainfall event is also recorded in the Archaeology Speleothem. Speleothem are cave deposits that you find, this Archaeology is in Karnataka near Karwa. Then let's look at the 1640 high rainfall. Now, then to support this 1640 event, we have tree ring data from Western India. And also, very interestingly, Archaeology Speleothem started growing around this time. That means it was heavy rainfall which favored the growth of Speleothem here in Archaeology cave. Now there are several proxy data from many parts of India that support whatever we interpreted with the susceptibility data. I'll give only one example because of shortage of time. This is the data for Archaeology Speleothem, delta 18O, stable oxygen isotope data, and susceptibility of our sediment samples. Look at the correlations, friends. It's 0.65. Ours is 0.65. It's very, very comparable to minus 0.62 and minus 0.61 of the Archaeology Speleothem data. Mind you, the Speleothem data are have very high resolution, whereas ours is not of such high resolution, but still, there is comparable. They can be compared quite well. So friends, what is the answer to the research question that I put in the beginning, the hypothesis? For that, we've seen a good correlation of susceptibility with rainfall. There are historical records to bolster the proposition, and we saw one, but there are several proxy climate data from other parts of India. Therefore, I'm inclined to say that magnetic susceptibility can be used as a rainfall proxy for tropical regions. So that is the answer to my research question. However, I must point out that all climate proxy data from other parts of India do not agree with our own data. What are the reasons? It's mainly the spatial and temporal variability of our monsoon. Even today, when the IMD predicts that there will be good rainfall for India, it will hardly be good rainfall. So the problem is, it will be good rainfall in certain parts of the country, but deficit rainfall in other parts, and flooding in certain other parts. So there is tremendous spatial variability. And also there is temporal variability. And that's the reason why there is no one-to-one correlation of our data with other proxy climate data. We also have geochemical data and also sedimentological data, but I'll only present some geochemical data. This is the iron to aluminum ratio. This is the terrigenous indicator. You see the close correlation between the two curves. That's susceptibility, that is, blue is susceptibility, that's iron to aluminum ratio. Titanium to aluminum ratio, again, good correlation. There are some very important proxies for chemical weathering. These are the ratios, and they reflect generally higher rates of precipitation. Why? Because in the tropics at least, chemical weathering is principally driven by rainfall, because temperature is more or less constant over several centuries or even a few millennia. Look at these curves for the three proxies for chemical weathering and the susceptibility data. Now they coincide or they are very similar. At least to my eyes, they are very similar. We did fact analysis or principal component analysis of the data. The first factor is the heterogeneous factor, which says that your signal, climatic signal, has come from continent, the catchment. The second factor is the pedogenic factor, which is equal to rainfall. Look at the close correlation between the pedogenic factor and the susceptibility curve. And the third factor is soil carbonate. As you know, carbonate forms when you have arid conditions or very low rainfall. So this is sort of, soil carbonate is sort of anti of rainfall or anti of pedogenic factor. And if you compare it with susceptibility data, susceptibility is blue and this is green. So it's not exactly anti-correlated, but it is quite anti-correlated. See here and there. Okay, ladies and gentlemen, now we have this susceptibility curve. We've shown that it is a proxy for rainfall. So if you take this as rainfall scale, low values mean less rainfall, high values mean more rainfall. Of course, we make certain assumptions that there has been no slumping of sediments and a couple of other things. But with these assumptions, we can reconstruct the past rainfall history for the 3,700 years that the large sample goes up to. So that's the age depth curve, mean sedimentation rate of about 1 millimeter per year. Let's look at the paleo-monsoonal variations based on the susceptibility data. So the rainfall increased in the past 100 years. And those are the low rainfall periods. And these ones, the high rainfall events. And please note, the lowest rainfall was during the drought period, and the highest was the 1640 high rainfall event that we looked at earlier, right? There was slight aridity in that period, but there was a much stronger aridity before 2500 kilo years BP. BP is before present, right? Friends, please note the strong aridity in that part of the sediment column, and that is before 2,500 years before present. And the very low rainfall here in the strong arid part corresponds to the rainfall that we got in the drought period. So you can imagine that it was a drought period prior to 2,500 years before present. Was there any cultural response to the climate change in Chitradurga region? Can you see these stones arranged in a circular fashion? These are megalithic structures that are found near Chitradurga and in another place called Brahmagiri, which go on to say, prove that human settlements in and around Chitradurga started only during the Shatavahana period, that is the 2nd century BC. But the question is, why not earlier than this? Why weren't human beings there in this region prior to this period? Simply because the reason is the climate was arid until this point, 1.55 kilo years before present. So it was very arid. And people will not live will not inhabit an area when there is no water. Right? So such were the unfavorable conditions in the area that there were no human settlements. Same with the Indus Valley civilization, deteriorated because of climate change. People were forced to migrate to other regions with favorable climatic conditions. The Akkadian empire collapsed, and the reasons attributed were political disintegration. The real reason was drought. Have a look at these data. There's a peak in dolomite, calcium carbonate, terrigenous strontium ratio, and tephra. All these go on to show that there was indeed a drought, climate change. And the Mayan culture also collapsed around 800 AD. The reasons advanced for this earlier were deforestation, overpopulation, warfare, and religious and social upheaval. But friends, the real reason was 150-year drought as revealed by the Kariako Basin sediments. So again, climate change. So that's the data. See the high titanium content here? That was a 150-year drought period. Okay, what are the implications of climate change? Humans have been profoundly altering the climate and environment in the recent times, particularly since the Industrial Revolution began in the 1850s. So all these examples that I pointed out earlier until now of climate change, do they ring a warning bell to us? Sometime tonight or maybe later, pause and ponder over this aspect, because it's important for our survival. Now, planet Earth will survive come what may. It's our survival that is at stake. Let's do the same exercise for the Pokot Lake area. So that's the susceptibility pattern. Those are the details, but I'll only point out the medieval warm period, which is a globally recorded climate signal, is also documented in our record here as low values of susceptibility. These are the low rainfall periods or events, and here you can see the little ice age recorded in the form of low values of susceptibility. Once again, little ice age is a globally documented phenomenon. This is Shantisagara in Karnataka. This is Asia's second largest lake. We carried out similar studies just to find out whether the story that I narrated is a cock and bull story or it holds water. It does hold water, as you can see here. The first curve is the susceptibility curve, and it goes back to 11,000 years, ladies and gentlemen. When we looked at the dates, we were really excited because no other lacustrine record, no other lake record from southern India has taken us back as far back as 11,000 years before present. That means practically the entire Holocene is recorded here in Shantisagara sediments. It also correlates very well with other types of data, oxygen-isotope and microfossil data, nitrogen, stable isotopes of nitrogen, solar, insolation data. Now let's look at this aspect. Is there any influence of the sun on our rainfall? Now for this we did spectral analysis. This is basically a statistical analysis of the data to determine cyclicity. And what did we find? We found that there is significant periodicity or cyclicity in our data. This is for the TK data. statistically significant periodicities of so and so years. Many are correlated with solar cycles. And the same with the second lake data, Pokot Lake data. This is again Pokot Lake data. See, these are the different peaks and troughs in the TSI, total solar irradiance. And this is our susceptibility data. I'm not saying that it is a 100% correlation, but there is a broad match between the two sets of data. So, with these data, I'm inclined to say yes, the sun does influence our monsoonal rainfall. So, at the end, I would like to conclude my presentation with these important points. Firstly, lake sediment susceptibility data is principally controlled by catchment rainfall. There is positive correlation between incidental rainfall record and susceptibility. This correlation is bolstered by historical records and proxy rainfall data from different parts of India. The pre-2,500 year BP, before present aridity, is supported by several paleoclimate records from Rajasthan lakes, Nilgiri peat deposits, and Western Arabian Sea sediment cores. Friends, please note that these data come from geographically diverse regions from and around the Indian subcontinent. So it is not just a speleothem here or a speleothem there. A large variety of data support this proposition. Hence, there is solar influence on our monsoon. And incidentally, this is the first investigation to propose magnetic susceptibility as a rainfall proxy in tropical regions. So I see a prospect of obtaining paleo rainfall data from thousands of lakes that dot southern India. And what are the future investigations that are possible that younger scientists can do? One is we need to prepare equivalence between magnetic susceptibility and rainfall. Like if I can say that so and so susceptibility value means so many millimeters of annual rainfall, that will be fantastic. We tried doing this, but by the time I retired, and I was not able to do active research, but this is one potential area where good work can be done. And it's going to help us a lot. Second, as I said, there are thousands of lakes and tanks in southern India. So we can carry out studies, similar studies on these lakebed sediments. We will have a geographically widespread data set on paleo rainfall, past rainfall. So whenever we do this, it will be like we have an all India paleo summer rainfall time series, because we'll have a number of past rain gauges in the form of these lakes. With all these things done, we should be able to better predict rainfall to the country. I wish to acknowledge the contributions of my then research students, but now holding good positions in different organizations and institutions. These are Dr. Prabhu, Dr. Anish Shwarya, Dr. Sandeep, and Dr. Shweta Shetty. Thanks to the DoD and now MOS for magnetic instrumentation and ISRO, GBP for research funds. I said this is a 3-in-1 shot. The first shot was sharing the research results of a new type of investigation which I just finished. What is the second and third? The second is, is this work template for good research? I think so. Let's look at another PPT. So I'm going to demonstrate with my PPT how this is a good template for doing some meaningful research, all right? Those are the slides that I used in the beginning. It's very important that we do intensive and extensive literature survey. When you do that, you'll be able to identify lacunae. You'll be able to identify knowledge gaps. That's very important before starting any research. And then you would like to fill this lacunae or fill these knowledge gaps. In other words, you are formulating your research question or hypothesis. We did that in the case of our research. And we chose appropriate sites. And we justified why we chose these two sites. Then choose appropriate methods. It's not that you use a certain methodology just because those instruments are there in my lab. No, that is not the justification. You should choose appropriate methods. If instruments are not there, then go to a lab where those instruments are there. Okay? So choose appropriate methodology and must justify the approach. You must convince yourself that the approach that you are taking is valid and is justifiable. And there should be a proper scientific background to your research. Otherwise, if it is not on a sound scientific footing, it won't stand. Then when you have the data, consider all possible interpretations. Do not be biased. So consider the different interpretations of the data and then discard whatever is not correct. And then test your hypothesis. We did this comparison with institute data, historical records, and proxy data. And then see whether your research question was answered. And then, not always you have all the data supporting what you found. There may be counter-evidence, there may be contradictory data. It's very tempting to ignore these data or, shove it under the carpet. Please do not do it. You may not be able to explain those data, but somebody else will be able to. So faithfully record your contraindications. Do not ignore them. You may yourself find some explanation to those data. Then look for supporting data, which will strengthen your hypothesis. We did that. And whatever data you got, what are the implications? Here the implication was to rainfall reconstruction and make connections with other branches of knowledge. It can be archaeology, it can be physics or whatever. Make connections. And place your data in perspective. We did all that. And yet another implication of the study, another supporting data, one more supporting data. Then it's very important that we do statistical analysis of the data that we get. The reason is statistical analysis will give you a different perspective of the same data. We look at the data through our eyes, through our brains. But, the insights that a statistical analysis provides is very different and it can be very enlightening. As I demonstrated in this presentation, for example, we were able to see the periodicity and the solar influence on monsoonal rainfall. So that's another implication we got because of the spectral analysis. And conclude, but also, you must look at the prospects for future work. The research that you do should throw light into the future, what is possible in the future, so that you can act as a guide to future researchers. And do not forget individuals and institutions for their help and support. So all that is the template for good research. I just put it down in one slide. Okay, 3 in one shot, first and second. What's the third? This PowerPoint presentation must have given you some tips to prepare your own PowerPoint slides. Very quickly, it's good to use dark background and light color font, 2 colors only, one font type, begin a font size so people can see it, preferably bullets, not full sentences. Otherwise, you'll start reading and showing your back to your audience. Not in a webinar though. No data tables, please, because no one will be able to read the data table. Use more figures and photos and less text. Use animation to your advantage. I gave a webinar on all these aspects on how to prepare PowerPoint slides. So if you're interested, you can go to YouTube and watch this video leisurely. Ladies and gentlemen, many thanks for your time and attention. That's my email address and mobile number. In case you have questions or points for discussion in the future. But right now, I'm available for discussion if you have any questions.
Thank you so much for such an insightful and inspiring speech, sir.
Pleasure always.
Finally, we are at the end of an extremely successful chain of webinar sessions organized throughout the span of 2 days, and I would request Professor Radhakrishna to end this session.
Yeah. Thank you, Professor Shankar, for a very enlightening talk through your valuable experience gained throughout your career. You have demonstrated most important, because I feel that this is the most important aspect for young researchers should keep in mind. All these salient features that you have brought into a very brief nutshell, you have made. I think these are extremely important for all young researchers. I'm sure that the participants would immensely benefit from your exciting talk. On behalf of the department, you are not new to us. You have been supporting, and during 2015 you supported us, and 2017 you supported us, and again, you are here with us, and we are very thankful to you.
It's my estimator, so it's always.
Yeah, I understand that, and then thank you very much. And then see you tomorrow. Bye-bye. Yeah.
Thank you for the opportunity. Bye-bye.
Bye-bye.
So,